is how many iterations converge. It depending on your initial guess. And that's why those are the reason that the conjugate gradient is not that good. But remember when you do the Cholesky, you don't have to provide the error norm. And you don't have to worry about the initial guess. You see? So each method, it has some good thing, it has some bad thing. Now.
Professor?
Yeah, question.
But how can you offer the error tolerance value?
Oh, that is up to you. If you want to have a very accurate answer, then you provide this number very small, right? But if you don't, you say, oh, I don't need very accurate, then just give 10 to the power minus 4. It's up to you, okay? Is that clear? Right? Now, this is the basic. It's nothing to do with research, but let me go a little bit deeper. Let me show you some more secret, okay? Now, let me ask you this question. According to my previous lecture, when I talk about the Cholesky, if I give you the matrix A, I give you a vector B, are you going to use the Cholesky directly here? Yes or no?
No.
Of course no. Remember? You have to transform this system into something new. Remember? And so that means in the last lecture, you have to transform this into a new system. Like A star times X star equal to B star. This is a new system, remember? How do you go from here to here? Remember you have to use Professor V.V. Kumar matrix reordering. Remember I-perm? Remember the I-perm? I-perm of the new number equal to the old number, remember? So you never solve this one directly, you have to transform it. Now, in the so-called conjugate gradient, you also do with a similar idea. Oh, by the way, I forgot to ask you. In the Cholesky, what is the reason that you want to go from A to A star? What is the reason? Why do you want to go from A to A star?
To
reduce the non-zero fill-in term. In other words, if you factorize Cholesky of this one, you have a lot of non-zero fill-in term. But if you do Cholesky on A star, then you will have a lot less. That's why it's benefit. Now, oh, what happened here? We do the same thing over there. We do the same thing. Now, but, so let me tell you very briefly, for the conjugate gradient, please listen carefully because this part we need to have some research idea in there. In the conjugate gradient, you also want to transform this system into something new, like A star. This is the unknown is X, right? Time Y, that's this guy, equal to B star. Okay? You have to transform from here to there. But let me ask you this question. For the conjugate gradient algorithm, why do you want to go from here to here? Is it because you want to reduce the non-zero fill-in term? No, that's not the reason. Because for the conjugate gradient, you always work with the matrix A. You have nothing to do with factorization, nothing to do with non-zero fill-in, right? So, what is the reason then? Why not you apply? Yeah. Why not Why not apply this conjugate gradient algorithm? Why not apply here? But we want to apply here. What's the reason? The reason is because the matrix A, in the beginning, it is called ill condition. Ill condition. Ill condition matrix. Do you know what ill mean? Ill means sick. Sick. And in mathematics, ill condition mean what? It means the eigenvalue of the matrix A, the eigenvalue of matrix A is very big. Very big. Actually, you remember I just reviewed for you how to find out the eigenvalue and the eigenvector. Remember, I just give you an example, right? Remember, if I have a matrix A, which is a 2 by 2, right? What do we get? Lambda 1 equal to some value, lambda 2 equal to some value. Remember? Right? Now, in general, if this is not a 2 by 2, it is an n by n, then you have lambda 1, lambda 2, up to lambda n. Okay? Right? Is that right? Now, let me give you some examples. Suppose you get rearranged so that lambda 1 is less than or equal to lambda 2, less than equal to lambda 3, blah 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 blah, less than equal to lambda n. You rearrange it so that that is true. Like for example, let's say lambda 1 is 0.3, lambda 2, for example, 12.98, lambda n, let's say, is 23,000, for example. So this is the largest eigenvalue, okay? And this is the smallest eigenvalue, agree? So the condition number, write out this one, the condition number of a matrix A is equal to what? Equal to lambda eigenvalue, largest one, divided by the smallest eigenvalue. Do you understand? So, the condition number of a given matrix A is defined by the ratio of the largest eigenvalue, like for example 23,000, divided by the smallest eigenvalue, 0.3. If the condition number, if it is big, then what does that mean? That means the matrix is ill. If this number is big, then matrix A is called ill condition. Ill condition. So that means if the condition number is big, that is very bad news. The matrix, we call it ill condition. Now, what does that mean? It means it will take you a lot of iteration to get the correct answer. Do you understand? So, because of that, what we do is, we don't want to solve this guy. We don't want to apply conjugate gradient to the original system. Instead, we want to solve this system. Now, after I explain to you, can you tell me what is the good thing about this guy? Okay. Do you want the condition number to be big or small? Tell me.
Small.
Small. The smallest, the better. Okay? For engineering application, any engineering application, usually this matrix is very, very ill, sick, which means the condition number is very big. So what we want is to transform this system to the new system with the hope that the condition number is much smaller. That's what we hope, is much smaller. That is the idea. So unless it is not like a Cholesky. In the Cholesky, you want to make this guy to have less non-zero Fueling term. Here, we don't care about the non-zero Fueling term. What we care is to make sure this matrix will have a good condition number, which means the condition number here is very, very small. Now, can you tell me what is the smallest condition number a matrix can have? What is the condition number is the ratio of the largest eigenvalue, right, over the smallest eigenvalue. What is the smallest condition number you can have? Actually, it's 1. The smallest condition number you can have for a matrix is 1. Why? Let me give you an example. Can you give me an example? What kind of matrix that will have a very small condition number? Identity matrix. Like, I say if the matrix A happen to be the same thing as the identity matrix. Identity matrix. Identity matrix means, you know already, right? 1, 1, 1, 1, 1 on the diagonal, 0 everywhere else, right? This is called identity matrix. So what is the condition number? Well, if the matrix A is the identity, you can see the eigenvalue will be equal to how much? Lambda 1 equal to lambda 2 equal to lambda 3, blah, 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 equal to lambda n equal to 1. They all equal to 1 for the identity matrix. So, because of that, the condition number of a matrix A, according to the definition, it is equal to what? The largest eigenvalue, right? The largest one, divide by the smallest eigenvalue, remember? So that means equal to 1 over 1, it is equal to 1. You know? So, to summarize it, the matrix A, for engineering application, you have a very big condition number, which is very bad news for the conjugate gradient. We try to transform into this system so that hopefully A star will have the condition number as small as possible. Now, we wish it to be equal to 1, but it doesn't have to be 1. It could be 10, 12, 100. That's okay, because it is still better than the original condition number. Do you understand? So now, the so-called $6 million question is, how do you go from A to A star? How do you make sure that A star will have a small condition number? Is that clear? So there are two ways to do it. Let me show you. And this will be related to the research topic. Let's go to this page. This is a key word. Preconditioning matrix. That's a key word, preconditioning matrix. Let me explain to you what does that mean. Okay, the very important keyword if you do Google search, right? Because after this lecture, you may do some Google search for your study. Preconditioned matrix. You see, The condition number is equal to the largest eigenvalue divided by the smallest eigenvalue, like I told you. Okay? So the way it works is, you start having this system to start with. Now, I assume symmetric and positive. Definite. If this is true, then you can apply conjugate gradient algorithm, the one I just described. Now, so I assume like that. So let's say precondition matrix. This is the most important question, okay? As a matter of fact, I can tell you, for the last 75 years, almost 100 years, researchers in the US and around the world, we always try to figure out how do you precondition the matrix so that the new system A star, X star equal to B star will have a better condition number. That is the most important thing. If you can do that, then not only you can publish a paper, you can write a proposal for Vietnam with government side, and I can also write a proposal too. Okay? But let me make sure it's clear. People around the world, researchers, already tried for 75, 80, 100 years. And they try with different ways to construct this matrix. Alright? And today I will try to explain to you one way only. One way, and then after that, depending on your creative, you may come up with an improved idea. Alright? So let me explain to you. So if you look on the screen, yeah, you see A is given, remember? A is given. X is the unknown, and B is given. What is this matrix P then? What is a matrix P? The matrix P, the dimension is also n by n. That matrix P, we call that is the precondition matrix. Precondition matrix. In our research that I'm going to suggest to you near the end of today's lecture, we will try to figure out this guy. Okay? And I will show you what is the relationship, what is the connection between this P and this new system. There must be some connection, right? Some relationship. So, if you look in here, this is P transpose. Am I right? And what is this guy? P transpose, and then you inverse. Is that clear? So, this is P transpose. Am I right? Transpose of a matrix. But what is P minus P mean? It means P transpose, and then you take the inverse. Okay? So, when you multiply these two, what do you get? You get identity matrix. Agree? Because when you take a matrix and then you time with the inverse of the matrix, it will be identity matrix. Nothing changed. Do you agree? Nothing changed. So here what I say is you start with A X equal to B. All I say over there is you say, alright, let's take A is here, and then you insert in here P transpose times P transpose inverse X. Nothing changed, am I right? Because this product is identity. You agree? Okay. Then after that, what do? You pre-multiply both sides by P. So here you pre-multiply by P, and on this side you also pre-multiply by P. Do you follow me? Okay. So that's why I got this equation. Now let's say you see this triple product, P times A times P transpose. I call it the new matrix A star. Remember? We try to construct the matrix A star in such a way that the matrix A star will have a good condition number. Remember? So this triple product, P, A, P transpose, we call it A star. Is that clear? This product, P transpose inverse times X, we give it a new name called factor Y. Do you agree? And then matrix P times the vector B, we'll give it a new name, vector B star. Is that clear? So now, assuming you know this matrix B, which is not easy, because if you can figure out this matrix B, I will give you some suggestion later on. If you can figure out this matrix B, then actually you become very famous. I can guarantee with you that. Very famous. But it's not too bad. Maybe if you work hard, we work hard, maybe we'll find out. Okay? But the point is, if, let's say, assuming we know how to figure out matrix B, then do you agree with me? You can construct the new system like this. Yes or no?
Yes.
Right? I assume a matrix B. And then later on I will tell you how to find the matrix B. Okay. But here's the good news. Remember, I assume the matrix A is symmetric, positive definite. Now be careful. Symmetric, it is a very nice property. Very nice property. So if the matrix A is symmetric, we prefer the new matrix A star still remain symmetric. You understand? Now, according to this equation, can you tell me what is A star? What? What is A star according to that equation? Can you tell me?
It's a triple product.
Yes, right. So according to that equation over there, we know A star is PAP transpose. P A P transpose. Agree? Now let me ask you this question. This matrix A is given, is that right? And it is symmetric. Is that right? P, it could be any n by n matrix. Alright? So my question to ask you is this. Is this matrix A star symmetric or not? You say symmetric? How about the rest of you? Oh, it is very easy to prove. How do you prove? Let's say if I give you a matrix, if I give you a matrix A, if I give you a matrix A, symmetric, right? I'm sorry, if you just give you a matrix A, how do you prove that it is symmetric? How do you prove? Well, if you say that A is the same thing as A transpose, then it means it is symmetric. You agree? So, what I'm saying to you is, in order for you to prove this guy is symmetric or not, right? Let's try to find A star transpose. Okay? Now, if A star is defined like this, what is A star transpose? Well, from algebra, you know the transpose will be equal to the product, but in the reverse order. So that will be equal to P transpose times A transpose times P transpose, right? Because the transpose of the product is equal to the transpose of each guy in the reverse order. Is that clear? All right. But because A is symmetrical, therefore A transpose is the same thing as A. Do you agree? Okay. Now you come to, oh, what is the transpose of the transpose? It's just equal to B. You agree? The transpose. So now you say, A star is this, A star transpose is the same. That means A star must be symmetrical. Very easy to prove. So, what I'm trying to tell you is that if your matrix A is symmetric from the beginning, when you transform it into the new matrix A star, try to keep it symmetrical. Don't lose that property. The only thing different is this guy is symmetric but very ill conditioned. That means the condition number is very big. Here you want symmetrical, remain, and small condition number. Alright? So now, let me explain to you how to find out the matrix B, which in the literature, the matrix B we call preconditioned matrix. Preconditioned matrix. Now let me tell you why this is important. Do you remember, according to my discussion, to solve the iterative method, how many methods you have? A lot. You have conjugate gradient that I just described for you. This is only for symmetric positive matrix system. You can have biconjugate gradient, or you can have GM-RES algorithm. Those are for unsymmetrical systems. Remember those things? There's a lot of different algorithms. But you know one thing? No matter what algorithm, no matter you do this or that, whatever, the most important thing is to find out this guy. Because if you can find out the matrix B such that the condition number here is small, then any method will be good, will be helped, will be improved. So this is my suggestion to you. Instead of doing the research, try to figure out the new iterative method. Don't do that. Try to find out the good precondition, because everybody will need you. Do you understand? That is the main thing. If you can come up, let's say, what is your name?
My name is
Tweet? Tweet? Okay. If you can come up with a new algorithm called Tweet algorithm. Yeah, that's good. But you only have a limited number of customers. But if you come up with a good precondition matrix, everybody will need you. Do you understand? Okay. So for the rest of the time, I just tell you very briefly how to get this matrix B. Just one way. And then after that, it's up to you. All right? Oh, so this is the way to transform the original system to a new system. You understand, right? In this way, symmetry is reserved. You still have symmetry in A star. But there's another way, but maybe simpler. There's another way. There's another way. Let's say you start with A. You know what you can do? From here, suppose you multiply both sides by B inverse. AX. This is another idea. B inverse. Do you agree? From here, you just multiply both sides by P inverse. Okay? Now, what's happening after that?